Check, 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 check. All right. Hello there again. Today I'm going to talk to you about pressure drop calculations for coolant flow through nuclear reactor cores. And we're going to be talking about pressure drops that we can calculate due to the fact that there's gravitational pull on the fluid, friction as the core fluid flows up along tubes here. This is a fuel rod assembly which would be placed in a reactor core. The fluid is going to flow up through this assembly. As it flows up through the assembly, it will encounter friction between the tubes, but it will also encounter friction at the spacers, which hold the assembly into its fixed geometry. And it'll encounter pressure drops at the entrance and the exit due to this fact that the flow has to squeeze into a smaller or expand into a larger area. The fact that there is some geometry changes causing friction as that squeezing of the area occurs, and due to the nozzle design to get the flow in and out of the plenum. So let me put this into slideshow mode, and we can get going. So here's a picture of a bundle, and again we have the bottom nozzle, which encompasses an area change and form loss. We have spacer grids holding the fuel tubes in place, and then we have a top nozzle, which is going to again cause an area. It'll be an area change, so there'll be some acceleration due to the area change. We have stuff in the way causing form loss or friction as the fluid moves through the stuff, and we'll have friction along the tubes. So that means that we have three longitudinal components in the assembly itself. We have the spacers, we have friction along the tubes, and we have gravity. And then at the entrance and exit, we have a change in area, a nozzle form, a nozzle configuration, and we have just due to the design of how these pieces fit together, we have some form loss due to metal that's in the way of the flow. So, if we look at incompressible flow, constant density, and we consider an inviscid case where we're going to say that we're not going to worry about the fact that some of the fluid along the walls of a pipe, for example, is flowing at a different speed due to friction with the pipe than the flow in the middle of the pipe. And if we consider that flow, what happens as you flow through a nuclear reactor core is you're going to have a number of area changes. You may have a large pipe that brings you out of the steam generator, where the liquid has transferred its energy in order to generate steam and become cooled down. It'll go through that pipe, and then it'll squeeze into the reactor and travel through the assemblies, where it heats up again, receiving energy from the fission reactions, causing the fuel elements to heat up and then transfer that energy to the fluid. And then it may come up to the top of the reactor core and enter a large exit plenum before going into another large pipe that leads it to the steam generator, and it'll go around in this circle. We'll have a number of different area changes and different pressure effects. So Bernoulli described the way that flow works with this equation here, and essentially we have an inertial term for the flow for bulk acceleration. We have various pressure drops due to maybe a pump placed at a particular location that might cause a change in pressure. across the pump. And then we have flow characteristics. We have gravitational effects, and we have acceleration effects. And these acceleration effects can be caused at different area changes, which is what's shown up in the blue diagram here. So we have our mass flow rate being affected by the area changes, and we have our gravity being affected by the elevation change as you go through reactor core. So, for real flow, the geometry of the inlet and outlet and the friction with surface features is really what causes a lot of pressure drop as you go in particular through the core of the nuclear reactor. So in reality we do have a compressible fluid, but it's just very slightly compressible. So we're really going to say, even for our real water flowing through a reactor core, we can treat it as incompressible with high accuracy. But it also is viscous. So there are friction forces for that flow. And there are two sources of the friction forces. There's internal friction caused by flow around abrupt area changes or through particular shaped metal forms. And then there's shear stress as the fluid tries to flow around itself. And then we have friction with the wall as you flow across a pipe. So the fluid has trouble flowing around itself to get around corners, but it also is affected by the wall itself. So both of these are friction losses, and they're accounted for right here. Pressure losses. We still have our area change, which is on the last slide. We still have our gravitational effect, which is on the last slide. We still have our pump pressure differential, which might be applied at any location from between the outlet and inlet of a pump, for example. And then we still have the inertia of the fluid, as it might if you have a non-steady state case with the mass flow changing. So I might just say our two perhaps simplest calculations for pressure loss in a nuclear reactor core are the gravitational effect and the effect due to the area change. So for gravitational effects, we just have rho g delta z. So the length of the core multiplied by density and gravity gives you the amount of pressure loss due to the gravitational effects of the flow up through the core. And then the fact that we come into the fuel assembly with one area for the flow and then have to squeeze in between the fuel rods, giving us a different area, allows us to calculate the pressure drop due to change in area, or the area change acceleration. Sometimes this is just called an acceleration pressure drop, but it's an acceleration pressure drop due to a change in area. Now, as I mentioned a moment ago, our friction force comes from internal friction factors and external friction factors. So we write it as the pressure loss here being a form loss and a friction loss, and those are those two green boxes down here. So for our form loss, we essentially have the flow coming into that form, or that maybe an entrance plenum, an exit plenum, or a spacer or something, some sort of feature change in the geometry. And it comes in with a kinetic energy. So we have what would be mv squared over 2, but we're dealing with the density here in our equation, so we have rho v squared over 2. And then we have that multiplied by the coefficient k, which helps us determine the form loss. And k is dependent on what the specific geometry change is. So this is something we can generally look up in a table for different types of geometry changes. Now, if you don't know the velocity, but instead you know the mass flow rate, you could calculate it this way, with an area, a mass flow rate, and the k that you look up as before. And then in a previous video, I derived how we can calculate pressure drop due to friction And we know how to get a friction factor for laminar flow. We know how to get a friction factor for turbulent flow. And then we're going to multiply that friction factor by the length we flow through, divided by the diameter we're flowing through, and our kinetic energy term. Again, if you don't know the velocity, but instead you know the mass flow rate, we can rearrange the equation and write it like this. So now we have equations for gravitational pressure drop, acceleration pressure drop due to area change, form loss, and friction as the flow flows through the reactor. Now, what's really happening in a reactor core is we're not just flowing through a pipe. We are flowing in between these fuel rods, and there are a lot of fuel rods. And there's some communication of the fluid in between the channels between the fuel rods. So what we do is we need to calculate an overall friction factor due to the fact that we have a number of channels communicating with each other. And that is what we're talking about here with bundle pressure drops. So we can calculate entrance and exit bundle pressure drops. And if you look in the book by Tadrius and Kazemi, you'll see a table and a figure that help us determine a number of different types of area changes common in nuclear reactor cores. And we again have our Bernoulli equation, and we're concerned here with the friction loss in Bernoulli. The acceleration loss, just rewritten here in terms of velocity instead of mass flow rate again, similar to what I did on the last slide. But I'm really concerned with this on this slide with the friction loss. So we had form loss on the last slide, and we had this equation. It looked just like this. We had this equation. It looked just like this. They look just the same, except that now we're going to have to look up K for a bundle configuration. And that is not necessarily a simple thing to do. So when you look it up, try to determine K. For example, the entrance plenum at the bottom of an assembly, or the exit plenum, you need to know the smaller area as it squeezes through the fuel rods and the larger area before it gets into the assembly. And that gives us this beta factor. Once you know beta, then you can use that along with the knowledge that you're at an entrance or an exit to calculate K. I believe I found it to come out to 0.19 when estimating with figure 9.6 in my case, for the homework problem that I assigned for my class. But this K can vary between 0 and 1. And then for the friction factor, this is the same equation from the last slide, except that this friction factor now is not the friction factor that we found in laminar flow for tubes or from turbulent flow for tubes. This is a bundle friction factor. So we have to find the friction factor using the bundle correlation, not a tube correlation. So let's look at that. Here we have a friction factor, which we're going to calculate for a rod bundle. So instead of our regular Reynolds number for tube flow, which we know how to calculate as rho v d over mu with the diameter of the tube, we are going to have our assembly Reynolds number, rho v d over mu again, but this is dE. This is the equivalent diameter. So the flow is in this white space here. It's not in a tube, it's in the white space. So we have to use the equivalent diameter here, or hydraulic diameter as it's often called. So I'm not going to talk about how to calculate that in this video, but I want you to be aware that when calculating the friction factor for a bundle, if you use the diameter of a fuel pin, you'll get the wrong answer, because we're not concerned with the diameter of the fuel pin. The flow is not inside the fuel pin. The flow is in between the fuel pin. So we have our adjusted Reynolds number using the equivalent diameter, and then we're going to have this constant derived from experiment for fuel bundles of common sizes, C, some friction factor. And we may have many different friction factors to determine. That's what the I is for, because there are different shapes of the channels. 1, 2, 3. Now, I've just shown the equation here to calculate CFI based on some constants, which you can find in Table 9.3 from the book, and the pitch, which is spacing between fuel rods, over the fuel rod diameter. So P over D is pitch over diameter, very commonly used quantity in nuclear reactor thermal hydraulics. Distance between fuel rods over, you can see it here, it's the distance between fuel rod centers, I should more accurately say, over the diameter of the fuel rod. So we're going to use that to calculate CFI, P over D, and the quantities from the table that you would look up for rod bundle configuration friction coefficients from experiment. So this slide is about how to calculate F, which we needed to calculate the friction factor, which we need to calculate the friction pressure drop. And lastly, as we move up through the fuel rods, we need to be concerned with spacers. So spacers are there to keep the fuel rods fixed in position so that they're nice and straight and they don't change position during the reactor operation. And to calculate pressure drops for spacers, we have a coefficient, a kinetic energy term, and an area ratio. So we have the unrestricted flow area away from the spacer, which is the area here or here between the fuel rods with no spacer there. That's AV. And then we have A inside the spacer, where the spacer takes up some of the space. So we have our spacer area here. So you'll see here on the on this diagram that I've got a fuel pin. I've got some space next to the fuel pin where the fluid can flow, and then I've got the spacer itself, which is the metal piece between the fuel pins, taking up some of that space that was available before for flow. So these are the equations to calculate the different areas, the areas as it flows between the fuel rods and the areas as it flows through the spacer, as shown right here. Now, those are the areas. We need to know our average velocity in the bundle, and then we're going to need to know our drag coefficient, which we'll find for our reactor cores in a typical rod bundle from Figure 927 in your book. Okay, so what we've done in this video is we have found how to calculate how to calculate pressure drops due to gravity, pressure drops due to friction along a fuel bundle, pressure drops due to spacers, pressure drops due to area changes at the entrance, pressure drops due to form losses at the entrance and exit to the reactor fuel assembly. And then one thing I didn't talk about here was the nozzle configuration. A nozzle configuration actually can be treated with the same equation that we did for spacers. So essentially we have a different geometry spacer down at the entrance, a different geometry spacer down up at the top, and then several spacers with another different geometry in between. So if we have the information about the geometry for the entrance, the geometry for the exit, and the geometry for the spacers, we can calculate the spacer pressure drop and the nozzle pressure drop. And that's it. That's how you calculate the components for pressure drop in a reactor core.